Okay, hi, my name is Victor. I'm recording this video as part of the assignment of the Machine Learning Foundations for Product Manager project. This video will have two parts. I will explain first the rationale, basically the approach, following the four steps that suggest in the group assignment, and afterwards I will share my screen to showcase AutoML and different queries that I use using BigQuery to train the models and the tables that summarize the evaluation of the performance for each of the models, for each of the algos. So, okay, let's start. The first question was modeling approach. Did you correctly identify the type of modeling task, features to use, and possible algorithms to use? So, I understand, one more time, the goal is to predict a continuous target variable. In this case, net hourly electrical energy output, and they give to us four different variables. So basically we have four different features: ambient temperature, exhaust vacuum, ambient pressure, and relative humidity. So given that the relationship between these features is non-linear, I understand that a non-parametric model should have a better performance, should have a big choice, should be a better choice. So since, one more time, I've been using Google AutoML, I picked Boost Tree Regressor, since it was it was in the list of the non-parametric tree models that were almost plug and forward. It was a bit easier basically to train and to launch, so I went for that. That was my first algorithm candidate, and the second was linear regression. So I mean, I choose it as a benchmark to compare the two algos performance, following the advice of the course materials, right, due to its simplicity. So question number 2, model building. Did you compare at least two different models, different algorithms, combination of features, or different hyperparameter combinations using a validate set cross of validation to optimize your model? So yes, as we said before, we used two algorithms, linear regression and boost tree regressor. I'll err as a baseline, and boosted regressor, I mean, it's an ensemble model, is supposed to be a better fit, for this problem. We train both using BigQuery ML with an 80-20 random trend test split. More or less what we should, what the course, as the course suggested. Model evaluation. Did you set a reasonable evaluation metric to determine the performance of your model and then calculate it on the test set? So yes, we choose three different metrics: mean absolute error, mean square error, and coefficient of determination. The results were surprisingly not too different. I was expecting a much better performance of boosted T regressor, but linear regression also made a good job. So for mean absolute error, linear regression had 3.59, whereas boosted T regressor had 3.01, around 20% difference. For a mean square error, the linear regression had 20.56, whereas boosted regressor had 15.68. Still, also boosted regressor outperform Aller here, and in the coefficient of determination, the outcome was actually pretty close. Linear regression had a 0.92, whereas boosted regressor had 0.943. The gap, as you can see, is not very big. I mean, less than 5%. For the coefficient of determination. And last but not least, model interpretation. Did you correctly interpret and clearly communicate the performance of your model? So I believe we did. The two models basically demonstrated a strong predictive ability. Again, I was particularly impressed with linear regression, since boosted T regressor was supposed to be a perfect fit for this problem, but as we can see, the performance gap was not very big. For both algorithms, we had very low error values. Both MAA and MSE were not very high, and there was a pretty high goodness of fit. So for the two models, the coefficient of determination was pretty close to 1, right? So I think that was a good performance. Time-wise and computing for performance, though, again, boosted regressor required a much higher computer power. So just to give you an idea, linear regression, we only required 1 minute and 42 seconds, whereas for boosted regressor, we require 16 minutes and 8 seconds, more than 10 times the amount, right? So conclusion, I believe that linear regression, I mean, if I had to repeat this very, very often, I think that, and if the goal basically is interpretability and speed, I think linear regression provide a much better performance and can be the best choice for the, at least for the database size given. If we do need extreme accuracy and interpretability is not a problem, then we can still go for boosted regressor, you know. Okay, thank you so much, and now let's share my screen. Hi, so this is the second part of the video, is where I'm showing AutoML, and in this case to train the models I used BigQuery. I strongly suggest to use BigQuery instead of running pipelines, because I mean I tried to run pipelines first, and it was much more difficult, and I entered a bit in a small rabbit hole. So I mean with BigQuery, the only thing to keep in mind is that whenever the variable AT is also a native variable of AutoML, so you will have to rename it in a different way, but for the rest it's pretty straightforward. So for both, you will only need 2 queries for each of the algorithms, one to create basically the model and to train it, and one more to evaluate the performance, right? Which is pretty straightforward, you know. And afterwards, this query will create as well one table when you will see the results. So I ran the 2 queries, one for each, the 4 queries, 2 for each of the models, and then it generated these 2 tables here, you know. So for boosted regression, basically in preview you can see the performance that I explained in the previous video. In general, we can see how the mean absolute error is one more time 3 for boosted regressor. For boosted regressor is better. It outperforming all the indicators, but as we can see, R square and the spline variance. But I mean, in general, the both algos performs very well one more time, but the difference is not very big. For boosted regressor is 0.94 and 0.94.3 and 0.94.7. For linear regression, we can see that is 0.92 and 0.92.5 as well. So I mean, at the end, it's pretty similar, comparing as well with the implementation time, right? So well, I hope it was useful, and thanks for listening.